Hello, good morning, afternoon, or night, depending on where you are in the world. On behalf of EMD International, I would like to welcome you all to today's webinar on WAsP-CFD in WindPRO. I'd like to begin by introducing our presenters and the topics that they will be addressing. First, we will have Morten Thureson from EMD International. He is manager of the CFD project. He will be discussing how WAsP-CFD works. After that will be Andreas Beckman from DTU Wind Energy. He is responsible for the WAsP-CFD model itself. He will be discussing why WAsP-CFD works. And then finally will be Lasse Svenningsson from EMD International, who is responsible for the WAsP-CFD validation effort. And he will be discussing, does WAsP-CFD work? Each section should take approximately 15 minutes or so, and then we will have a 10 to 15 minute question session at the end of the webinar. So we ask that you please submit your questions in writing in the questions section to the bottom of your GoTo interface. You can expand the questions section by clicking on the plus symbol just to the left of the word questions, and then type the text in the window that appears there. Questions will be answered by the appropriate person during the 10 minutes to end, so please try to write the name of the person to whom you want to address the question in the question itself, or at the beginning or end of the question. If we do not get to your question, don't worry. We will be sending out a link to the Q&A summary as well as a link to the recording of this webinar to all attendees within the next few days. So without further ado, I give you to Morten Thureson with how WAsP-CFD works. So please take it away, Morten.
So thank you, Nathan, and welcome to this presentation on how WAsP-CFD in WindPRO works. Since all of you attending this webinar are WindPRO users, we will assume that you are quite familiar with annual energy yield calculations in WindPRO, but of course also that you are curious on how WAsP-CFD calculations works within WindPRO. During my presentation here, the next 15 minutes, I'll try to answer the following questions. What is WAsP-CFD? How is it implemented, and what are the benefits? What do you need to run WAsP-CFD? What software and resources will you need? How do you get CFD calculation credits? How do I make WAsP-CFD AEP estimates? What is the calculation workflow? And this will be highlighted with a real live demonstration. And then finally, I'll end up with give a little introduction to what will be news in the next release expected here early 2014. So, what is WAsP-CFD? If we are to keep it very simple in 3 simple punchlines, it is as simple as this. It is a fully automated CFD solution. It is a cluster and cloud-based CFD solution, and it is as easy to use as WASP. Let's dig a little more into this. I just said that it's a fully automated CFD solution. So what does this mean? It means that the area of interest are calculated each in tiles of 2 by 2 kilometers in size. The actual calculation domain is of course much larger than this, typically about 15 to 20 kilometers from your site. But the accurate flow corrections for your area of interest are always returned to you in these 2 by 2 kilometer calculation tiles. Automated also means that the calculation mesh is generated automatically while you are uploading your height contours and roughness lines to the calculation server. Then those are automatically converted into a calculation mesh. Automated also means that convergence is ensured automatically. No flow results will be returned to you except in the case that the strict convergence criteria has been fulfilled. I also said that it's a cluster and cloud-based CFD solution. So what does this mean? It actually means that parts of the analysis are done partly on your own PC, and partly the computational heavy part of the analysis is done on a high-performance computer cluster. So what is this heavy part? It is calculating the flow characteristics, the speed-ups and wind wear over the terrain. It's done by sending the terrain data to the high-performance computer cluster hosted here at EMD in Denmark. And what we actually are setting up is your height contours and roughness information, and we'll return the flow characteristics back to you. Why are we using this high-performance computer cluster? We do this because it's much faster. A calculation on the high-performance computer cluster will last about 30 minutes for these 2x2 kilometer tiles, and this should be seen in light of if you are running on a traditional PC, then it would have lasted maybe a week or so to do a similar calculation. It's important to emphasize that it's only the terrain data that's sent to the cluster. All wind data are always kept on your own PC, so it's easy for you to update the analysis with new wind data just by running calculations locally on your own PC. As I also mentioned, WAsP-CFD is as easy as to use as WASP. By design, it requires exactly the same user skills as a traditional WASP analysis, and largely it also applies the same workflows and modeling procedures. The WASP-CFD model takes the same input as a traditional WASP analysis, some terrain information, orography, roughness, classification, obstacles, and some information about the atmospheric stability. In WASP-CFD, it's the two models for flow corrections due to orography and roughness classification that has been replaced with the ellipsis 3D CFD model. But all the other models remain the same. So the stability model and the obstacle model is the same as in a traditional WASP analysis. When you're doing a WASP analysis, a traditional classic WASP calculation in WindPRO, and you want to add on a CFD analysis with WASP-CFD, the extra workload compared to that is typically less than a few hours time. 1 or 2 hours is what that requires. So let's have a look on what you need to run WASP-CFD from within WindPRO. First of all, you'll need to have access to the latest releases of the softwares, WASP 11 and WindPRO 2.9. Both of these versions was released in April 2013. Then you'll need to have some calculation credits for the CFD cluster, and also you'll need to have access to some of the energy modules where you can consume these CFD flow results. And actually most of the energy modules in WindPRO that we have down here on the screen will be able to consume the WASP-CFD flow results. Let's assume that you already have WindPRO and WASP 11 installed on your computer and you want to get started, add some calculation credits. You need to add those to your cluster account, and this can be done in several ways. You can order it from the EMD homepage, emd.dk/windpro/ordering, or you can email or call our sales department. When you've done that, you'll receive a quote, and you can see down here, this quote here, I've asked for 5 calculation credits, each costing 200 euros per credit. Then you need to pay, and you can pay either by credit card or bank transfer. And when the payment is complete, the credits will be transferred to your cluster account. It's a process that may take 1 or 2 days to complete, so if you have any mission critical calculations to be made, we recommend that you pre-order some credits to store on your account. They don't expire. So, ready to do the presentation, the live demonstration. What I'm going to show here this afternoon or morning or whatever where you are, I'm going to make a WASP-CFD AEP estimate, and I'm going to set up and start a CFD calculation. I'm going to show how the download of the CFD results are done, how you can view the speedups on the map, how to run a StatGen to generate a wind atlas or wind statistic, and then run a weight loss or park calculation within WindPRO by using the standard N.O. Jensen weight model and also the CFD results. So now I'll do the live demonstration. Just a second, for I need to switch into WindPRO here. So this is the project that I'm going to present today. We have 11 turbines here and a mid-mast located in the southwestern part of the site. It's a site in Northern Ireland. It's a mountainous terrain, so it's perfectly suited for doing a CFD analysis. In order to set up the CFD, WAsP-CFD calculation, we'll start by entering a site data object. I'm adding that to the map right now. And I set the purpose down here for use in CFD calculation. I'll just rename it CFD calculation 2013. I'll go to the Map, Files and Limits tab here, and I can see that I have linked the roughness lines and the height contours in this site data object. Now I just press OK. Then I right-click on the symbol for the site data object and I'll put it into edit mode for CFD areas there. And then I'll right-click on the map and I can add a CFD area or CFD tile. And I'll do that right now there. And you can see I have a tile here on the map, and I'll move that into the position. I'll add a few more here. This is tile number 2 or area number 2, and I'll add one more, tile 3 and tile 4 there. So in this case we have 4 areas covering the whole site. I'll just remove the edit mode for the CFD areas. And actually now we are ready to do the calculation. So now I go into the calculation window of WindPRO, and here we have the WAsP-CFD module. So I'll click that. I'll name the calculation CFD calculation 2013 demo. And down here I can select the site data objects with WAsP-CFD purpose. And in this case we have only one that I just created, and we have 4 CFD areas defined. I can move into the calculation tab, and here we have the 4 areas listed. All are selected. Here I have the high performance computer cluster at EMD. I'll log into that. When you purchase a WASP 11 license, you'll automatically have a cluster account on this high performance computer cluster. Well, now we are about to start the calculation. I can click here, down here, start selected. Okay. And I can press the calculate button, and here it asks me which calculations credits I'll use. I'll use this. I have 13 credits left. I'll just press OK, and I'll press OK. So right now it'll be merging the map files and preparing to send the height contours and the roughness information to the high performance computer cluster. Right now we can see the state here that the 3 of the areas are already started, and the 4th one here is in queue and will be completed here later this evening about 8 o'clock or so. When the actual calculation has completed, you receive an email with a notification that now you are ready to download the CFD results. And what you'll do then is simply to go back into the calculation that you created and press one of these download results button, or there will also be the button down here will be enabled so you can download all selected jobs. So it's pretty easy to do. Okay. The next thing I'm going to show is when I've already pre-run the calculation here. I'm going to show that. I have down here, you can put all the calculations into a result layer in WindPRO. And here you have the 4 tiles that I have run a little earlier this week. And an interesting thing with what we are seeing here is actually the speed-ups with calculated based on winds from a northern direction. I'll just show the legends so you can see it here. We have speed-ups in the range from 0.8 to 1.5. Each of these 4 tiles are actually individual and fully independent CFD simulations. So an interesting thing for consistency is to check whether the borders here, where the tiles are actually overlapping, whether it gives a similar result with smooth transitions. And as you can see, the speed-ups are moving from one area to another in a very smooth way. So this should be a demonstration of that it's actually a very consistent and robust way to do a modeling of a large domain. Good. The next thing I'm going to show is how to do a wind atlas or wind statistic. I'll go back into the calculation window of WindPRO, and I'll press the StatGen module, and I'll just write a name, CFD demo 2013. And here I can decide whether I want to use a site data object created for WASP or CFD results. I'll choose to use the CFD results. I'll go into the StatGen tab, and I'll select the flow results that are calculated in the area where I have my mast. And this is, in my case, it's area 1. I want to use the 40-meter anemometer, and I'll just name the wind statistics CFD demo 2013 and press OK and calculate. And it should last no more than a few seconds in order to do the calculation of this wind statistic. Let's see. Well, while we are waiting here, I can say that it's when you are working with WASP-CFD, and you, let's say, assume that you want to share your result with some other colleagues that you have, it's very easy to just make an export project in WindPRO and then send all the CFD flow result correction files to your colleagues. So that's really easy to share. Now, okay, now we have the StatGen calculation, and we want to do a park calculation also. I'll just press the park calculation, and I'll say CFD demo 2013. I'll go into the VTGs to ensure that I have the right 11 turbines selected. I'll go into the wind distribution tab here and check I want to use the CFD results files, and then I can add the CFD. I have the 4 flow results files here for each of the 4 tiles. I'll just open those. Now they are available here. I'll go into the wind statistics tab here, and I'll choose to add the wind statistics that we just created here, and it's available here, CFD demo 2013. And we need to link each of the 11 turbines to the nearest wind statistics. There we go. And we can just inspect that the settings for the air density and power curve are also correct. Okay. Start calculation. And this will last about a minute or so to do the WASP-CFD analysis using the flow models from the CFD model and the standard NO Jensen weight loss model. It's exactly as you're used to with a traditional WASP approach. While we're waiting on this, I can say that when you have a traditional WASP analysis where you have maybe height contours or roughness classifications in ranges, say 10 kilometers from your site for the orography, and maybe 30 kilometers for your roughness classification. For the WAsP-CFD, you will need to have orography in a slightly larger range, but we have added a nice little feature in the line object where you can press the extend button, and then you can easily extend your existing local height contour lines with SRTM data. So this is something that will take you about a minute or so to extend your local height contour lines with 5 kilometer or 10 kilometer of extra orography from the SRTM shuttle radar topographical mission data. So a minute's waiting time here for doing the part calculation, and we can just inspect the results. We have here the 4 tiles and the layout for the turbine, and we can see down here that we have an annual energy yield of 181 gigawatt hours a year and a very high mean wind speed for this particular site. So I think actually this completes my live demonstration, and I think I'll just continue with a small outline on what we expect in the next release of WAsP-CFD and WAsP-CFD in WindPRO. What we're working with right now is adding siting parameters from WAsP-CFD into our site compliance module, and we expect that to be finalized here early 2014. DTU is working on a detailed forest model where the canopy impact can be included. Of course, you can still do forest model with WAsP-CFD as it is right now, but with a more basic displacement height approach as you're used to in WindPRO. What will come is also some alternative subscription models. Right now we have only the option of selling one tile for 200 euros, but there will be subscription-based models also, and also a model where you can have your own in-house cluster solution. Just to brush up what I just did, I've showed you how to set up a CFD domain with these 4 tiles. I outlined how to download the CFD calculation results and ran a WAsP-CFD StatGen and a part calculation. It all took less than 15 minutes, or maybe about 15 minutes, and as you saw, no CFD expert skills were really required. So you may ask yourself, how is this even possible, and what is inside the box? And this will be the topic for our next presentations. Back to you, Nathan.
Thank you very much, Morten. For those of you that are submitting questions, we are handing them off to the correct presenter. If we don't get to your questions at the end of in the Q&A section, then don't worry, we will try to get to them in the Q&A summary in a couple of days. So without further ado, I give you to Andreas Beckman from DTU with why WAsP-CFD works. So take it away, Andreas.
Yes, thank you very much, Nathan, and thank you for giving me this opportunity to do this presentation today. So I'm supposed to talk about why it works, and here are some of the names from DTU Wind Energy that has been part of it, and also some of the companies that have taken part in the development of this. So let's see if I can make it work. So why it works. I've decided to choose to split this question up into 2. First, I will answer why WAsP-CFD, and secondly, I will try and answer how it works. So let's get started with why. So first, why do we want to use CFD? Okay, so here I have a slide with a lot of information on it. What you can see up here on the top right is a picture of a small hill called the Bolon Hill. We did an experiment a couple of years ago on this hill where we positioned some masts and some measurement equipment You can see the red dots here, the measurement locations. What we did was we invited people for a blind comparison to try and predict the results. That's what we are seeing, some of the results over here. So on these two plots we see speed-ups on this x-axis. And the speed-up is the difference between the wind speed at this reference mast location in the water, and for the left plot it's this location down on the beach. And on the right plot here, it's the location just on the edge of this escarpment. And on the y-axis, you have height above terrain. And what you can see here is that all the different models that participated in the blind comparison, they predict the speed up quite good here on the location on the beach. They predict the speed down here, as you see. But for this position, the position on the edge of the escarpment, you see that the measurement says that there should be a speed down. But the linearized models, they predict a speed up, while these blue curves, they kind of predict the speed down. So sorry for this. So what we see that for complex terrain like this particular site, it seems like CFD can capture some more physics. I also have these are some average errors on the speed up, and we can clearly see these are for all the locations on this Bolon Hill. And it seems like these RANS model, they did very well, these CFD models. They were able to reduce the errors. So why do we want to use CFD? Well, that's because we see these improvements in complex terrain. So we want to be able to simulate complex terrain accurately. But then you might ask, why do we want to use WASP? Well, here's the same picture as Morten showed, the classical WASP methodology method. And the boxes you have in the middle, that's the models, flow models. You have, in WASP, you have models that can predict what effects the houses or obstacle has. You have roughness models, and you have terrain models. And so this is basically what so we have the CFD model, or we have what we call the IPZ model. That's the classical linearized model. So what CFD and the IPZ model does is to calculate the effect of these roughnesses and these terrain heights. But you cannot just have a flow model like this on its own, because like we saw on the previous slide, your flow model will only give you speed ups basically. In order to calculate wind resources, you need some kind of wind measurement. So, and you need a methodology to combine your wind data, your measurement, with your flow models in order to get your wind resources. And this is what WASP does. So you cannot have a CFD model by itself and calculate wind resources. That's what you need. You need WASP to do that. So why do we need WASP? That's to do AP calculations, to do wind resources. So the original question was, why do we want to use WASP-CFD? Well, this is a punchline, that we want to be able to do accurate wind resources anywhere, so in both complex and less complex terrain. So how does it work? Okay, let's start with this schematic again, where we have the site description in the middle, the red boxes. So the first, we do two assumptions when we do the CFD calculations. The first assumption that we do is that for the actual CFD calculations, we neglect stability and Coriolis effects. So we don't have any temperature effects in the actual CFD calculations. And the reason why we do this is that by neglecting these effects, the flow becomes independent on wind speed. They become Reynolds number independent. The CFD simulations only depend on your terrain and roughness. So by doing these assumptions, it's possible for us to separate the two. We can separate wind data and we can separate the CFD simulations in two. So that means that you can do your CFD calculations even before you have any wind data. And then as you add wind data, wind statistics, you can keep doing your wind resource analysis. So yeah, and the other assumption that we do with the CFD calculations is that when we do these tile calculations, as Morten showed us, we are also calculating a mean large-scale roughness, this reference roughness. So we actually have a representative roughness. So we categorize our CFD speed-up calculations using this reference roughness. And thereby we can do CFD calculations that are done independently of each other, and they can later on be connected via this reference roughness. So that means that you can do CFD calculations where you have your meteorology mast, and then you can do a completely separate simulation at the place of your turbine position, and you can do the wind resource analysis. So these are the two assumptions that we do in order to use CFD for wind resources. So when Morten sends the CFD files to the cluster, all the CFD is happening automatically. So I'll show you what's actually going on the computer cluster, what's going on the black box. So this is an example where you can see a site here. This is a site from New Zealand, from Wellington. And what's inside the red curve is actually the map that was sent to the cluster in this exercise. And the blue position here was the coordinates that the user specified should be there. The user was me, but that's the position where we wanted the tile. You can see the 2 by 2 kilometer tile here. So that's the information that the cluster does. And the first thing we will do in order to do the CFD calculation is to prepare the terrain. So I will see if this works. So here you see that we have prepared the terrain for CFD. This blue circle is 34 kilometers in diameter now. So that's the extent of the computational domain. So this is the part that we want to simulate. And you see that here in the far field, the terrain has been flattened. I can go back and forth between the pictures. So this is the original one. And outside the red curve, we have no details on the terrain. So that's why it looks strange out here. So I can go back and forth. You can see how the terrain has been massaged or flattened. And we do that because we want to apply simple boundary conditions at the edges. We want to have simple logarithmic velocity profiles. And again, what we are really interested in is the difference between our far field velocity and the velocity at the site of interest. So we want to have nice, well-defined far field velocity profiles like that. Here's another example. That's a mountains terrain, and we can see how the terrain has been prepared for CFD. So the far field terrain has been flattened like this. Okay, that's step one. The second step for the CFD is to make the mesh or the computational grid, and this is the most important thing of any CFD simulations. So well, you see here we have the map again, and this is what the computational mesh looks like seen from above. What you can see, we have this polar mesh, and I don't know if it's very clear, but the grid cells are refined toward the center. Here you have the highest resolution, and they are coursed towards the edges. I can zoom in on the mesh. So this is about 15 kilometers and 6 kilometers. And you see in this inner domain, the resolution is constant. This is 3 kilometers, and this is about 2 by 2 kilometer. That's the tile that was specified. And you see that we have very high resolution in areas extending this. You can zoom in. This is about 1 kilometer, and in here we have 20 meter resolution, and it's not horizontal resolution, it's resolution along the terrain surface. So if you have a vertical cliff, as the example I showed you with Bolon, the grid cells, you have the resolution down the slope of the terrain. So it's very high resolution in this region. I can also show you how the mesh is in 3D. Again here, I hope this visualizes the high resolution that we're having. Near the ground, the vertical resolution, or actually the resolution perpendicular to the surface, is only about 5 centimeters, and then it coarses as you move away. What you can also see is that the grid lines, they are not extended up vertically, but they are perpendicular to the surface. And this makes higher quality CFD grids, because the cells are following the computational grid cells are following the terrain and are not skewed, and that helps us when we want to have the actual solution, and it also gives us better solutions. So we have very high resolution, and let's try and zoom out again. And this is the final domain, computational domain. And here is what the mesh looked like for this mountainside, again zoomed out, and this is zoomed in to the same 1 kilometer extent. And I would like to have shown you many more grids, because that's one of the main things about any CFD simulation is to have good quality grids. And this is the part of this automatic CFD solution that I'm most proud of, that it's actually possible to generate these high quality grids automatically. So yeah, I hope you get a good idea of this. After having generated the grids, we have to run the actual simulations. And the CFD code that is running on the cluster is the Ellipsis code, which is developed at DTU Wind Energy. DTU that was formerly called Risø National Lab. And it's a code that has been developed for more than 20 years. And we are about 20 people working on the code daily. And we apply it for other fields than terrain. We're also using it for aerodynamics and rotor simulations. It's a traditional finite volume solver, but it has been parallelized very efficiently so that we can utilize the computer resources effectively. So each time a user sends a request for this 2 by 2 kilometer squares, the CFD grid is generated, and then 36 wind directions are simulated. So one 2 by 2 kilometer tile calculations is actually 36 CFD simulations. So we have very high resolution grids, but we also have very high resolution, so like angular resolution. So we do all these wind directions independently of what your actual wind direction is. And that's because in complex terrain, just small wind direction changes can have big effects on your flow results. So you need high angular resolution also in order to keep, And we use third order quick schemes to discretize our what do you call it, convective term in the Navier-Stokes equations. So we use higher order schemes also. We use the K-epsilon turbulence model, and we solve our CFD. We solve the CFD problem to a very high degree. So this is a low residuals that show that we are converting the each CFD solutions to a very high level. So having done 36 CFD simulations, we actually throw away more than 99% of all the results, because we are only returning the results, even though we have them in the entire domain, we are only returning the results in this inner 2 by 2 kilometer area. It's actually a volume, it's 300 meters high and 2 by 2 kilometer. So inside this volume, we send the speed up factors, we send turnings, and we'll soon send turbulence parameters back to WindPRO. So, and the reason why we are only using the results in this inner layer, that's because, as I showed you, this is the region where we have the highest resolution. It's a region where we have the highest quality results. So in order to do wind resources, even small numerical errors can be very bad for wind resource analysis. So we are really aiming for the highest quality CFD results possible in order to lower the numerical uncertainties. So results are sent back. So that was kind of why it works. So I'll just make a summary of what I talked about. So WAsP-CFD is really designed for complex sites. So you have high risk number sites. And I showed you the different, how the CFD works. And it's a whole method. It's not just CFD. It's a whole method that has been developed in order to be able to use CFD results for resource calculations. And because we have moved it to the to the computer cluster, we can make quality CFD. We can make high resolution grids. We can make high resolution, as you saw, at many wind directions. We can do high quality numerical schemes, and we can converge our solution to a very high degree. That's very important because we want to use it for wind resources. Secondly, because it's all automatic, it also means that results are consistent and they're repeatable. So any user can get good, consistent CFD results. And like Morten showed you, the results are also shareable. And that means that it's not the CFD user doesn't just develop a CFD report that he gives a finished CFD report. You get the raw CFD results that you can import into WindPRO or WASP. And that means that you can change your turbine layout and the CFD results are still valid. You can get more wind data input and your CFD results are still valid. So it's another way of working with CFD results than we're used to. It's only if you change your map details, your topography, then you should redo your CFD simulations. Otherwise, they are still valid. Finally, you now have two independent flow models in WindPRO. You have what I call the IPZ model, which is the traditional standard linearized models, and you have the CFD model. So by having two models, you can get two independent results, and that helps reduce the uncertainty of your wind resource predictions. So that was the end of my presentations. If you have more questions, then we can have now in the questions session, or that you can type in. You are very welcome to write me. That concludes my presentation. Back to you, Nathan.
Thank you very much, Andreas. If you have questions for Andreas, please be sure to mention that in the text section when you write the questions, so we know to address those questions to him. And now I give you to Lasse Svenningsson with the final section, Does WASP-CFD work? So now over to you, Lasse.
Thank you, Nathan. And hello, everybody. So as Nathan said, the presentation of my talk is WASP-CFD, does it work? And the contents that I'll be showing you is the validation effort that we've done here at EMD. And actually, the picture that you're seeing right now is taken from one of our validation sites. So how did we approach this validation? Well, we made a long list of test cases that we wanted to run, and then we grouped them into two groups. So one group we called classical cases, and these cases are either theoretical studies or studies from the literature. And the second group we named reference cases, and these are test cases which are real wind power sites with measurements suitable for model validation. And talking about model validation, how do you validate a flow model? And in the following slides, I'll be showing you a lot of RMS errors. And this is a standard performance measure when you do model evaluation. So RMS means root mean square. And if you have a number of observations, and for each observation you have a corresponding modeling value,
you can take the difference and apply this equation, and you'll get one number, which is the RMSE, the RMS error, which is a measure of your model performance. So the three classical cases I'll be showing you here are a speed up, which is a theoretical study where we analyze the speed up as a function of terrain slope, and a study where we reproduce the results of this, what I call the original delta Rix site, which was the site that was used to develop the delta Rix method, which is a correction method for WASP in complex terrain. And the last classical case is the Askerveen Hill experiment. So first classical case is this speed up versus slope, which is also called the mascot study, and it's based on a publication by a Japanese group which used their own CFD model called mascot. And what they did was that they defined 5 200-meter high cosine hills, and they varied the width of the hills from 8 kilometers to half a kilometer. And so the resulting terrain slopes vary from 3 degrees to 39 degrees. And for each hill, they modeled the speed up and extracted the speed up at 50 meters above the hilltop, as indicated on my figure here. So what does this result look like? Well, let's first take a look at WASP. This graph shows you the speed up on the y-axis and the terrain slope of these cosine hills on the x-axis. The blue curve here shows you the WASP speed ups for a particular roughness level. So how do these compare to WASP-CFD? Well, the results for WASP-CFD are shown here in the red curve for the same roughness level. And what we notice is that the speed ups are very consistent at the low terrain slopes, whereas as we go to the higher terrain slopes, the WASP speed ups are much higher than WASP-CFD. So how do these results compare to those published in the original study? Well, the original study looks something like this. Again, speed up on the y-axis and terrain slope on the x-axis. So what is interesting in this plot, or perhaps what is a little curious, is that there's a crossover, which is not what you would expect theoretically. So we looked into how can you actually get such a crossover. And one obvious thing is to vary the roughness, because as it turns out, the speed up factors depend on the roughness level for the CFD model, but also for the WASP model, which might be a surprise to some. So what if we also plot the speed ups for WASP but use a different roughness level? We get something like this gray curve, and if we take away the blue one, we get something which looks more like that original study. But what we have to keep in mind is that we are comparing speed up factors for two different roughness levels, for WASP and for WASP-CFD. So as a conclusion for this comparison is that when you compare WASP-CFD with WASP speedups, we don't see a crossover. That is, if you use consistent roughness levels as input to WASP-CFD and WASP. And so the speedup factors of the two models are consistent at low terrain slopes, that is slopes less than 10 to 15 degrees. And at higher terrain slopes, we see much larger speedups using the linearized model WASP, as we would expect. So the second classical case, which I call the original delta Rix site, it's a site in Portugal called Aveiro Viseu. It has 5 10-meter masts in quite complex terrain, as illustrated here. And I've indicated the Rix value, which is a measure of the degree of terrain complexity. Actually, it's the fraction of terrain within a 5-kilometer radius that exceeds a terrain slope of 17 degrees. And so with these 5 masts, we can make a number of cross predictions. Actually, if you include the self predictions, which I indicate here by the red arrows, we can do 25 cross predictions between these masts. And so what if we plot the cross prediction error versus the difference in ruggedness index, or the difference in terrain complexity? We get something like this. So we have the logarithm of the cross prediction error on the y-axis, and we have the difference in ruggedness index on the x-axis. So this is a classical delta Rix plot, and each blue dot here represents a cross prediction between two masts. So it's what we see is that there's a strong correlation between the cross prediction error and the difference in terrain complexity. So what if we do the same thing for WASP-CFD? We get these red dots, and what we notice immediately is that there is a very poor correlation between the difference in terrain complexity and the cross prediction error. Actually, if you make a linear fit, it's horizontal. So if we are to conclude on this classical case, we see that first of all the maximum cross prediction errors when you compare WASP-CFD to WASP, they reduce to just 1/4, and this strong correlation with the difference in terrain complexity between the two masts that you cross predict between, that's fully relieved. The third classical case is the Askervane Hill experiment, and that was an experiment conducted in the 80s, and the particular data set that we were studying was conducted during a period of neutral stability, and they had measurement equipment measuring at 10 meters in a transect across the hill, and measuring a profile at the hilltop. And at the same time, they had a reference mast measuring at the same height here, and here at the bottom left you also see a cross-section of this almost idealized hill. So let's first have a look at the results of this transect at 10 meters across the hill. So we have the speed up relative to the reference mast on the y-axis, and the distance across the hill on the x-axis. And the green curves show you the measured speed-ups, the blue curve shows you the WASP speed-ups, and the red curve shows you the WASP-CFD speed-ups. And so obviously the position of these curves is quite sensitive to the reference point. So we chose the upwind reference point, but we could also have chosen a reference point on the profile. But what turns out is that if you take the overall DRMS error here and compare it, it's not very sensitive to this reference point. And what we see is that the RMS error is reduced to 1/3 when you compare the WASP-CFD speedups to WASP. And in particular, the lee side, where you have more of the nonlinear flow effects, is much better handled by WASP-CFD. So let's have a look at the hilltop results. We have the speed up relative to the reference mast on the x-axis and the height above ground level on the y-axis. And the measurements are green again. WASP-CFD is the red curve, and WASP is the blue curve. And again, we see a better consistency of WASP-CFD with the measurements. If you sum that up, again, as a coincidence, we see a reduction of the RMS error that the RMS error of WASP-CFD reduced to 1/3 compared to the WASP-CFD RMS error. And in particular, the speed-ups near the ground are handled much better by WASP-CFD. And that's where you have the strongest speed-up effects. So that was the classical cases. Let's proceed to the reference cases. And so we set up a number of selection criteria to boil a long list of sites down to relevant sites. So we wanted sites with complex terrain, at least 2 masts measuring on site, at least 1 year of concurrent data with an acceptable quality, but we also needed acceptance by the project owner to actually use the data. And we prioritized a large geographical spread. So eventually, unfortunately, we ended up with just 6 available sites. But that was prior to doing any calculations. So let's have a look at the main result. So if we took the top level anemometer for each mast and tried to predict the top level, the measurements at the other top level anemometers for each site, that's the result I'm going to show you next. Why the top levels? That's because that's typically close to hub height, but that's also where we have the least measurement uncertainty, because usually the top level anemometers are mounted more carefully and with less flow distortion. So this graph shows you the RMS cross prediction error between all masts at the top level for each of the 6 sites here shown on the x-axis. The blue curve shows you the RMS error for WASP. So let's have a look at how that compares with WASP-CFD RMS errors. So that's the red curve here, and as you see, for all 6 sites, we see a significantly lower cross-prediction error for WASP-CFD. And the improvement, which is the difference between the blue and the red curve here, shown as the green curve, is actually quite consistent for all 6 sites. And if you to sum up that, so we see a reduction of the RMS cross-prediction error, which on average is 0.3 meters per second for these 6 sites. That translates to a reduction in cross-prediction error of 4% on mean wind speed, which would translate to a reduction in prediction error of 6 to 8% on annual energy production. So let's look at these reference cases in another way. Let's take the top-level anemometer for each mast and see how well can we predict the lower levels. So those results are shown here. On the y-axis shows you the RMS error for the profile fit, and on the x-axis we have the result, we have each mast. And so again, WASP is the blue curve and WASP-CFD is the red curve. In this case, the picture is more scattered, and you would say on average the performance for the profile fit is comparable for WASP and WASP-CFD. And what I have to mention here is that we actually used default stability settings in all cases, both for WASP and WASP-CFD. So one thing to conclude from this is that profile fit is not a good indicator of the performance. So because just before we saw a significant reduction in the cross prediction error when we compare between the top level anemometers, and that's the most important modeling error because typically we measure close to hub height. So if you have just one mast and you look at the profile fit, that would not be a good indicator of how well you can predict other positions at your measuring height. And another thing is that this profile fit is strongly dominated by the WASP stability model, which is the same for WASP and WASP-CFD. In particular for default settings. What we saw is that if we adjust the default stability to site-specifically for each of these sites, excuse me, the improvements of the WASP-CFD tend to stand out more clearly. But that was beyond the scope of this evaluation. So the last analysis I'll show you for the reference cases is that for 3 of the cases, it was possible to fit all masts within just one tile. And so, for instance, for this site on the left, you could see that our baseline calculation, we had area 2 centered on a mast and area 1 centered on a mast, and we could compare the cross prediction error to a calculation where we have both masts in area 3. And so this allows us to assess the tile dependence of the WASP-CFD results. So, and that's what I show you here. So again, we have the RMS cross prediction error on the y-axis, and the blue curve here shows you the cross prediction errors for WASP. The red curve shows you the cross prediction errors using the centered tiles, and the green one using the all masts in one tile. So you see there is a small dependence here on the tile configuration, but what we also need to emphasize is that it's significantly less than the improvement compared to WASP. And another point here is that this site, which stick a little out on the left, it's an extreme case in several regards because it has an extremely steep coastal cliff with tall trees, and the masts are positioned at 3 and 6 kilometers inland. So we have multiple strong complexities here. So that's not really representative of many situations. So in conclusion for this last analysis is that there is a minor tile dependence for WASP-CFD, but in all cases analyzed, it is significantly smaller than the improvement in prediction accuracy that we see compared to WASP. So getting back to the title of my presentation, which is WASP-CFD, does it work? With these test cases that I just presented to you, I feel quite confident in answering that yes, it works. And just to emphasize our main result, so we saw a reduction in cross prediction error when you compare to WASP of 4% on the mean wind speed for WASP-CFD. And if you translate that to annual energy production, we see a reduction of cross-prediction error or prediction error of the annual energy production of 6 to 8%. So thanks for your attention, and back to you, Nathan.
Thank you very much, Lasse. Much appreciated. That concludes the presentation portion of the webinar for today. However, we will go into about 10-minute or so question and answer section. Greatly appreciate all the questions you have written. We'll get to as many of them as we can. But for now, I will give you back over to Morten Dursen to answer a couple of the questions that you've submitted. Thank you. And take it away, Morten.
Yeah, thanks, Nathan. I have a question here regarding whether it's possible to arrange the tiles in a different way than what I showed in the demonstration earlier on, where we have 4 tiles in this very rectangular setup. So we might just use 3 tiles and to get the same results. And actually, this is one of the neat features with WASP-CFD, that you have the option of totally arranging the tiles in a totally independent way. So you have one tile centered on your mid-mast, and then if you have, say, your wind farm layout along a ridge, then you can have tiles that covers the ridge. You don't need to have any overlap between tiles, or you can have space between tiles. It doesn't really matter, as long as you have a tile at your mid-mast where you can calculate a wind statistic or wind atlas. So so I think that in my case there, with the demonstration project, we could have settled with only 3 tiles for that project. I have another question here regarding any limitations on the modeling area, how large the modeling area can be. And there's really, with the setup that we have, where we are calculating these 2 by 2 kilometer tiles, there's really no limitation on how large the modeling area can be. Here at EMD, we have calculated a site with, I think it was up to 100 tiles. Of course, it will last a little longer to do such a simulation, but a strength of this approach is that since it's made up by individual calculations, then you can expand the calculation area to almost any domain size. I think that is what I'm going to answer right now. Back to you, Nathan.
Okay, I can see I have the microphone now, so I will see if I can. I have a couple of questions also, and one of the questions I have regarding the CFD model is whether, for instance, the obstacle model is part of the CFD model. And I can tell you that the obstacle model is at the moment not part of the CFD simulation. So what the CFD model does is to calculate the effect of the terrain, the height contours, and the roughness only. But by removing effects like wakes also, that means that we can do these simulations at that they become independent of wind speeds. If you wanted to include, for instance, wakes or temperature effects in the CFD calculations, then you would also not only do 36 wind directions that I showed you, but you would also have to do each wind direction at different wind speeds, different stability effects, and so on. So that would be quite many CFD calculations. So by even though we are still doing 36 CFD simulations, we have managed to keep the computational effort down by making this split. Yeah, so should I take one more question? Yeah, well, I have several questions with this, with the wind speed, and again, for instance, what wind speeds are we simulating, are we using when we do the CFD simulations? And the simulations are actually done with a logarithmic profile that has 10 meters per second at 10 meters height. But the CFD, the speed up factors that we are calculating, they would be exactly the same if I did it with 1 meters per second or 20 meters per second. Because we have removed these effects, they are completely independent on what wind speed I'm simulating. So I think that's the questions that I will take now, and I will try and answer the other ones in the following days. So back to you, Nathan.
Thank you very much, Andreas. And finally, we will hand it back to Lasse Svenningsson to answer a few questions.
Thank you, Nathan. So I have two related questions here that I'll try to answer in one go. So the question is, if profile fit is not a good performance indicator, which indicator is then better? And you say, if we have measurements close to hop height, a very good performance indicator, you could say, that indicates, you could say, how will you perform on the errors which are most important to your prediction, is how well can I predict between two masts which measure at or near hop height. So the cross prediction error between these two masts would be a very good indicator of how well can I predict the wind climate at all my different turbine positions. And so the related question here is that, well, if profile fit has not improved, does it mean that it's even more important now to measure at hop height? Well, a comment to that is that in our setup, we deliberately used only default stability settings. And what I also mentioned, perhaps just briefly, is that we can actually improve the profile fit if we had adjusted the stability settings. And that's a post-processing. That's not something that you do before you do the actual calculation on the CFD cluster. So you can, once you've done the CFD calculation, you can actually play with the stability parameters, and you can improve your profile fit. So the answer to this is no. Of course, it's always a very good thing to measure as close to hop height as possible. So I recommend that in general, but these results do not imply that it's mandatory, because we could have gotten better profile fit if we had wanted to adjust the stability parameters for each of these sites specifically. Yeah, so that's it. Thanks for the good questions, and I'll also reply to the remaining questions, and they will be put in our Q&A. So back to you, Nathan.
Thanks a lot, Lasse. And that's time for today's presentation on WAsP-CFD and WindPRO. I hope you've enjoyed it. Please look forward to some information from us in the next few days, which will include a link for this video and also the Q&A summary for all the questions that were submitted, not just the ones that we got to. And yeah, so have a good day, evening or night, depending on where you are in the world. Thanks a lot for your time and attention. Goodbye.